Hello, welcome to Meet the Scientist. Happy fall. We had a slight hiatus, but we're back and we have a new scientist in the hot seat tonight, so we're excited about that. So I wanted to start by first announcing, and maybe you've been following some of our social media posts, we did have a giveaway pushing for more users on our YouTube account. And so we have some winners, and so I wanted to announce the winners to start. So the winner of our 1,000th YouTube subscriber goes to Ryan Bradley. All right, so that's the 1,000th YouTube subscriber. And then we picked 3 randomly, and that would be subscriber names Natalie Aulis, Sangeeta Roy, and Cyborg Ninja. All right, so tomorrow, somebody from CSI will reply to your video comments with further instructions on how you can get your prize. We thank you for liking us, following us, and we hope you will continue for good videos like this. So again, welcome to Meet the Scientist. This is your opportunity to meet a few of our scientists here at CSI, get to know a little bit about them and some of their research. And it's a great opportunity for us to highlight some of the work that we have going on here at the Coastal Studies Institute. So tonight we have Dr. Teresa Ryan. Dr. Teresa Ryan is an engineer. She's actually in the Department of Engineering at East Carolina University. Although she is out here, and this is probably our newest faculty member out here at the Coastal Studies Institute. And so welcome,
Hi.
Teresa. We appreciate you being here, appreciate you sitting in the hot seat. And I get to ask you all kinds of questions, but the key is for us to get to know you a little bit better, get to know your science a little bit better, and I think the community certainly likes to see what we're doing.
Yeah.
So, I think it's always fun to get a little bit more information just about your background, and I think you have got a really interesting background to where you came to your position, not necessarily just here at CSI, but ECU generally. And so I wonder, clearly your background is engineering, but I wonder if maybe you'll speak to your trajectory. And, you started with an engineering degree at Georgia Tech.
Yep.
And then went out into the workforce.
Yeah. I guess looking back and thinking about how do I tell my story to somebody new, there's been more than a little bit of serendipity along the way at several points. But so I got my mechanical engineering degree from Georgia Tech and ended up in medical device research. I knew I wanted to have my mechanical engineering degree, but I had interest in how can I apply that to medical applications, and ended up in a couple different startup companies, the first of which was looking at how to do non-invasive, like needle-free monitoring, specifically glucose monitoring. If you have diabetes, you have to check your sugar, and this was one of the early technologies of how to do that without involving a needle. And then that led to a second one using the same sort of technology, the same needle-free stuff, to do drug delivery. And so those two different, very small, very exciting research companies were sort of that first part of my professional career.
But it must not have had everything you wanted.
It
right?
didn't. And here's where one of those fortuitous things, all along I enjoyed teaching. I was a marching band person all through high school and college, and so I had always taught part-time. And when the second company, this was at a time when the biotech investment bubble kind of crumpled and companies started falling left and right, and I found myself without a company. And I took the chance because I had always sort of thought, well, maybe I'll go back and teach. Maybe I'll go back and be the wacky high school physics teacher. And much earlier than I thought I would, I had that chance. So I was certified alternative certification, went into the classroom in Georgia and taught in 2 different high schools there and really loved it. It was a lot of fun to get high school students excited about science.
And you spent 6 years doing that?
4 years at, well, yes, 4 years in high schools actually teaching and another couple years doing the band stuff.
Right.
But while I was there, and this is one of those, you have no idea how the trajectory is going to spin. One of the high schools hadn't had a science fair in, recent history. I was like, oh, we got to have a science fair. And so the chemistry teacher across the hall and I said, we have to have science fair. It's a must.
Right, sure, yeah.
And we got the science fair rolling. And then the next year, the science fair again, helping these students get excited about answering some question and doing the work and starting that process made me realize, okay, hang on, I miss answering questions myself. It's like, okay, it was fun and exciting to get the students into it, but I miss doing it for my own curiosity and my own questions. So that's when I took the sort of later in life detour to go back to graduate school.
Yeah.
And I moved to DC, sort of looping back when I was an undergrad at Georgia Tech. I had worked in an underwater acoustics lab and been a research assistant there and connected back up with some of those colleagues who had by that point had faculty positions there, and went to graduate school to do acoustics and vibrations.
And so what's interesting there, I mean, first I love the trajectory, right? It does show you that, it's okay to sort of take this circuitous approach to a career. And, and you've since 2013, you've been at ECU within the Department of Engineering and doing great stuff, which we'll talk about this evening. But it's not this straight path of this is what I know I want to do.
No, I sort of quip sometimes and say, you can make it up as you go along, but to some degree it's true. It's like I've again, serendipity and just kind of going with how things evolved, it has ended up making sense. And I would like to say that I started with this great grand plan of where I was going to end up, and it's not that at all. It was okay, let's do research, let's do teaching, and then, okay, I guess this is converging me on a faculty position, because what do faculty people get to do? They get to do both.
Yeah.
And so it's now I love my job. It is both of those things.
Right. And what isn't another interesting thing, I think, is the different, not just the different occupations, but the different things that you've worked on, right? So starting sort of at your first, I guess, real job,
The
working on
biomed.
biomed, and now you're sort of working in coastal systems, although obviously there's a thread of certainly engineering that goes through all
Right.
of those. And so I guess start there is what really, I guess, piqued your interest in engineering from the get-go, and that sort of thread that's gone all the way down.
So when you're in the state of Georgia and you're pretty good at math, where do you end up going
There's
to
Georgia
college?
Tech.
You go to college at Georgia Tech, but there was one more factor there is I had a fantastic older sister who had already blazed the trail to Georgia Tech.
Interesting.
And so it was kind of easy to unwittingly, I mean, at 18, I don't know, you just kind of go with what seems to make sense.
Sure.
But the fact that my sister had done that before me made it that much easier to say, yeah, this makes sense, and this is kind of how to make it work. And at 18, I had no illusion of knowing what I really wanted to do. And so you're picking between things that are very general, things that you can do a lot of different stuff with. And that's sort of picking between mechanical and electrical. Engineering and electricity seemed a little scary, so I went with So I went
Can
with
be.
mechanical because I did know that with a mechanical engineering degree, you can do lots of different stuff. And so I've done biomed, I've done, I guess the military connection that we'll talk about is sort of another common theme.
Yeah, so let's talk about that. So how would you encompass your research themes that you focus on within your group? I mean, the interesting thing, although maybe I'm giving too much away, is one of the things I think is interesting is you said as an undergrad you did some acoustics and you worked as an undergraduate lab technician or undergraduate technician. And that sort of led you toward connections for your PhD.
Absolutely.
Which is pretty interesting considering some of the work that you're doing today, which is giving
It's
some of that
kind of
away.
the same.
Right? But yeah, so how would you, if you were to give a general overview of your research interest, what would you say?
So at this point, it's acoustics and vibrations. It's how do moving mechanical systems, how can you use mechanical vibration for many different things. And I've got a couple different projects that are related to that aren't really coastal in nature. And then that's the vibration side of it. And then there's the acoustics side of it, which is the work that's primarily based out here. And the work that I do with acoustics is understanding how the really complex environment out here where you've got complex air currents, complex situation where the water, the land, all of that comes together to make a pretty messy picture of the noise and trying to better understand that.
And you mentioned that you have this sort of military connection, right? And so I'd be curious, so where's the connection, why is the connection, and why are they funding you?
Why are they funding me? So this is the what's this project about?
Yeah,
question.
what's this project about? This whole
All right.
mess that
that I'm
is
trying
the
to
coast.
unravel. So let's say that you're standing on the beach, and this is the bigger picture, not necessarily yet why the Navy is interested in it, but you're standing on the beach and there's a boat out offshore. Can you hear it coming? Can you hear the boat? And what is it about the winds, the shape of the dunes, what the sea state is, all of these things play into whether or not somebody standing on the beach can hear the boat coming. And being able to have a mathematical model, you've also probably seen a fish finder. If you're on the boat, you want the information of, can the person on shore hear me? And so the research we're doing is going to eventually let the Navy build a can you hear me box instead of a where's the fish box.
I like the way you sort of boil that down, right? So it is simply put, right? When do you hear me?
Can you hear me?
Yeah.
And that's valuable
And that changes depending on all of those parameters you talked about.
It changes in a really unpredictable and complicated way. And so bit by bit, we're working on, okay, how does the wind affect it? Okay, how does the sea state affect it? How does the moisture in the soil affect it? And that's one that we had undergrads out at Jeanette's Pier digging out sands that we're going to see what the moisture content is and have done measurements to see how does sound interact with wet sand, with dry sand, with sort of in-between sand. So it's piece by piece understanding all of the things that play into the question of, can you hear me coming?
And so how do you do that? I mean, walk us through some of the instrumentation, right? So although it might sound simple, right? But there's
a
wet
lot.
versus dry, right? I mean, all of this that might play into it, let alone the instrumentation you have to use to do some of these measurements.
So there's a lot of moving parts. We fill up a U-Haul truck when we are doing our experiments, because I guess the other thing is that my collaborators at Catholic University, they're the ones that are mostly working on the math side of it. trying to get the computer models. And then my primary job is to go out and make measurements, and we look at, do the measurements match the math? If they don't, we tweak the math, we do more measurements, and we're just looping around until the math that they've got match what we measure.
Actual observations.
And so what do we have to make all of our observations? We've got masts that are about as tall as a 2-story building, that we put the masts and we put microphones on the masts. We've got speakers, obviously. We got to make noise.
You got to propagate sound.
And we can put the speakers out on a boat so that we put the microphones on land in a particular arrangement. We put the speaker out on the boat so that we can make very controlled noises. We're not really listening for boats yet because we want to have a very, very simple sound to look at how it changes as it goes. So that's the sound and the recording of the sound. But then we also have to have a lot of information about what's going on with the weather. So we've got ultrasonic anemometers that we put on other masts that measures very, very precise wind speed. Which way is the wind going? Which way is it swirling? We've got several different UAVs, little drones that we put on programmed flight paths that go up with sensors that are recording temperature, pressure, humidity, time, and position, so that we get this really cool map of what's going on with those parameters while we're sending sound.
And so your UAVs, so drones, right?
Yeah.
Small drones are essentially, they aren't there collecting, I mean, again, most people are using drones for collecting imagery. These actually have instruments
Right.
mounted on them, so they're actually collecting some sort of atmospheric parameters for you.
They're collecting all of they're collecting the very local weather conditions. No pictures.
Right.
And so, we've got the drones in the air, we've got microphone stations, we've got the noise out there, we've got the weather anemometers, and then I'm very excited about a very cool new toy that we're going to get fairly soon.
Scientific instrument.
No, toys. I have all of the cool toys.
Come on, typical engineer.
I do. I have a whole truckload of cool toys that I get to play with. So the coolest new toy that I get is a skyward-looking LiDAR. So another laser device that will allow me, instead of, right now I have 4 of these anemometers that measure wind speed, but that means I only have 4 pieces of information of what the wind is doing. The wind can be doing all sorts of different directions, patterns, swirling. Again, you've been outside, you see a piece of paper and it...
Right, sure.
We need to understand that. And so this LiDAR lets us basically scan a whole cone of the sky and understand what the wind is doing in a big chunk.
So it's not just a point or not just a column, but actually a cone.
It's a whole volumetric cone of wind gradient information. So that's going to be a cool one to add to what we have.
And so I imagine another thing you have to consider is, well, the type of coastline, or maybe even the sinuosity of that coastline, or are there buildings on that coastline, right? All of those would come into play as far as sound propagation.
Absolutely, because you know, perhaps if you have moved recently, that when you suddenly take all the furniture out of your rooms, your house sounds weird and echoey. Or if during wintertime, if there's a train track that's kind of close to your house.
Or say a bypass,
Or
not far from your house.
But when the trees lose all their leaves, what season it is, how much foliage there is, how wet or dry the foliage is, what kind of, is it a pine tree? Is it a dense, do the dunes have sea oats on them? Do the dunes have little low grasses? Are the dunes bare?
Is there a point where some of this begins to, I guess, overlap such the models that are being developed, the numerical models that ultimately the Navy probably really would like, that you don't need to necessarily go out and measure every sort of possible scenario, that they do start to sort of converge on a model that would be very predictive.
That's the hope. That I guess we're trying to collect all of the information so that we can then start to understand which parts of it do we really need to know. Because if you have all of the parameters, and like you say, how good can the prediction be if we start having less information? Like, can we get good enough information from a satellite picture to not have to be there beforehand?
Yeah.
For topography,
That's
for the moisture, for whatever thing may influence it, how can we get that information without having to go look at the scene beforehand?
Yeah, what I think is also interesting about the study is the iterative approach, right? So you're collecting those observations, and independently there's this model being generated, and then you could look at these two things independently of one another, and then go back to the drawing board and really think about how one influences the other, as opposed to building the model simply based on the observation. But they seem to be a little bit independent of one another.
And independent, and also we have to look at each of these influences and sort of really understand, okay, what does temperature do? Okay, what does humidity do? Okay, what does the wind do? It's like all of these things may make it louder or quieter. And so understanding each small influence starts to let us put the puzzle pieces together.
One of the things that's pretty fun to see when you come out and do your research, at least the research you're doing out on the coast, is the army of students you bring along. And so, you mentioned that what your job allows you to do is sort of the teaching aspect, the research aspect, and what you've done a fabulous job of being able to do is marry those two things.
Yeah, thanks.
And so maybe speak to what that does for you, what it does for your students, and maybe if you had a feel for what the students really take away from something like that.
I think that plays into one of the reasons that I picked ECU in the first place, because this was a very much undergraduate-centric, teaching-centric program, and that was important to me. And because I had such a positive experience as an undergrad research assistant, I knew I was motivated to try to do the same thing once I was in the position to do so. So it is part of what I've tried to really establish and work towards. And what do the students get out of it? They get such a real confidence in understanding how to tackle a problem. And one of the things, this semester is one of the first times that I've done a special topics research course. So I have a team of 4 students. They're the ones who were out here at Jeanette's Pier last weekend, that they are now, and it's sometimes really hard, but I give them the big picture, this is what we need to do. Okay, now you guys figure out which gear do we need, what's the schedule, the whole logistical side of it. And it has been fantastic watching them sort of sort it out. And
with prompts, is it totally independent? And have they, we often learn from our failures, and so have there been failures?
In this class so far, last weekend was our first trip.
Okay.
And we had everything we needed.
Oh, that's important.
Which has not happened in some trips in the past.
That others have led.
Maybe
I wasn't going to say it.
that maybe I was the one that should have double checked that we had everything. It happens. But no, so far they have done, these are also students who've been working with me for at least a year.
Okay.
So they are pretty familiar
Been in the
with
field with you as well.
with what we do. But yeah, it has been really cool to see them really dig in and, figure out all of the little gory details, because there's so much that goes on that administrative and logistics side that will translate whether they end up doing research or end up in some other engineering position. Everybody's got to be able to look at a bigger project and break it down and make a sensible plan to meet the objectives.
Yeah.
So that's been really cool to watch. The class has gone really well so far.
So far. It's still early.
It is still early.
I think that's one of the things that's exciting about ECU's engineering program is that real connection with the students, that opportunity for the students to work very closely with faculty, to get those opportunities to do research, and with some of the faculty to actually get in the field. I mean, truly in the field, right? Not just the field could represent the lab, but this really is right.
No, this is get your feet dirty, get your feet wet field work.
Yeah.
And I think that the teamwork and the synergy between them is one of the rewards. And some of, speaking to what I think this does for them generally as a group of students, I have students that, because of the experience in my lab, one of them went on to graduate study at the Air Force AFIT and is now at Wright-Patt. She's at the research lab there. And I have several former students who are at Cherry Point as engineers. One of them in the vibrations, doing vibrations analysis stuff there. So seeing them have that confidence and that practical knowledge of how to do experimental work gives them a leg up on people who only did coursework.
Yeah. So one of the things, first, for those that are watching, if you have questions, go ahead and type those in, because we want to get some real world questions from you as well. I've got plenty. I don't know if they're real world or not. But one of the things that you've mentioned in the past and sort of we spoke about in our recent newsletter, go check it out, was this idea of you being a bridge. I really like that analogy. I don't know if you brought that up. I really thought it was interesting how you do offer these many connections. And so this opportunity, when it came up for you to come out to the Coastal Studies Institute a bit more permanently, was really exciting for me, bridging this gap between different departments, looking for opportunities to collaborate. And I don't know, I just wanted to give you an opportunity to speak to that idea of bridging in your research and maybe some of the other things, including your teaching, clearly.
So sure, there's many aspects of it, and actually, again, this sort of looping or iterative thing, if I rewind a little bit to that biomedical work that I did with my first job, I wasn't termed the bridge there, I was kind of termed the glue. Because we had 5 or 6 engineers and then several people on the medical side, because we actually did do clinical studies of the things that we were building. And I was kind of the designated go-between that dealt with the medical side and the engineering side. And so making those connections or those bridges, I guess, is something that I've kind of always done. But now bringing that back to present day, there's so much appropriate expertise out here that people on main campus in the engineering department may not even be aware of some of the similar or some of the opportunities to merge what we're doing. We also have many, many students who can benefit from, and projects, our senior capstone course sequence, their last year is some big project, culminating engineering project. And several of these are looking to possibly use the wave tank facility.
Right.
And we're also looking to bring online this master's program in coastal and environmental engineering. That is going to be a huge benefit for the students who are going to be primarily housed on main campus, but they need to be able to make these connections and get these authentic experiences out here.
Right.
It's going to benefit, again, faculty on both sides of this. Our students are going to be able to have experiences out here. Faculty out here are going to be able to take advantage of the perspective our students can provide. There, in so many ways, it makes sense, and it really is this interdisciplinary work that's where the cool stuff happens. You can't just stay in your one tiny area and do, in my opinion, and do really, I don't know, groundbreaking, exciting stuff. You need those other perspectives.
I think that's what's exciting about what we're doing out here is the group of people that we have with the very different disciplinary backgrounds, sort of bringing them together in this melting pot of coastal science.
It is. And you have to have different fundamental expertise to understand all of this complicated stuff. Just like you have to have wind information and topography information and temperature. You have to have all of these different pieces of the puzzle to understand the acoustics. You need all these different disciplines to understand the complex stuff going on out here in many different dimensions.
And so to try and start wrapping it up, because I do try to keep this to 30 minutes, as people behind the cameras laugh. One of the questions I really like to ask, because we do have different audiences and how these videos are used, is for those sort of the budding engineer, the young mind, whether at the high school or maybe even before, or maybe an undergraduate, any advice you would give to them? And I think coming from you, given your background, I think could be really telling.
What's the advice? I guess two things. One, don't be afraid to redirect.
Parents, it's okay.
Don't be afraid. Go for it and take a risk on something that seems interesting and go for it. But keep asking questions. That's the thing. Keep curious, keep asking questions, and be persistent about it.
And one of the things that from your past, it seems like you were never afraid to, get into something, whether it was the undergraduate research assistant, right? That actually led to much of what you're doing today. So getting involved and really engaging.
Yeah. Jump in.
All right. A couple questions.
Oh boy.
So first, fascinating research, and thank you for your contributions to the engineering profession. Must be an engineer. What are your thoughts on how we can attract more women to engineering studies and careers?
That's a tough one.
Yeah.
It's a tough one, especially being in mechanical engineering, because it's still one that is sort of conspicuously low in percentages. And I think it's just an issue of, at least for me, being an example and trying to make sure that the female students get the opportunity to see what a successful female engineer looks like.
Having good role models.
And how to reach that. It's the, first robotics. It's the technical STEM activities to get involved with at the younger ages and fostering that and sponsoring that and making sure that somebody is advocating that, hey, you come here, here's a screwdriver.
Right.
Come put this together.
Yeah.
But yeah, I approach it from the perspective of helping make sure that the students that I have influence with or access to know that they're welcome to come play with the toys that we
Right.
have.
I think that's important, and again, as you mentioned, having that role model, so they can see themselves in the position.
Well, and I had the role model of my sister.
Right.
I mean, it is kind of the phrase is escaping me, but I don't know, the follow-on
Sure.
makes it easier.
Right. And so, thinking about your acoustic research, we sort of spoke to, I guess, more of the military applications. Are there other coastal applications that you could apply some of this work towards?
City planning perspectives, I think understanding better how sound moves in this complex environment would help target noisy bypasses and how to well,
Maybe.
how to mediate that, or
should
how
talk.
to how to understand how increases in traffic, increases in boat traffic, increases in vehicle traffic, understanding how that would impact new developments or new roads, or how do you divert. So understanding that, and also potentially using some of the same techniques to monitor natural sounds. But I think primarily understanding how the human generated sounds would, again, from a city planning perspective.
Yeah, no, I think that's interesting, particularly as we continue to develop some of our coastal systems. All right, well, so first let me thank you
Sure.
for joining us. Dr. Ryan can be found here at the Coastal Studies Institute. You can find her on the website. If you have more questions for her, they could get in touch.
Yep.
Your inbox might blow up.
Sure.
We appreciate you joining us. I hope that you will find us next month for another Meet the Scientist, and we will see you soon. Thank you again.
Sure. It was fun.
It was fun. I learned a lot.